Hi everyone, we're Team Saturnus. We're working on the unmanned aircraft system for greenhouse purposes for Bayer Crop Science in Marana. My name is Madeline Jones and I was the team leader and mechanical engineer.
I'm Gabe Unruh. I was the purchasing lead and a systems engineer.
I'm Lucas Wojcik. I'm a biosystems engineer.
I'm Carlos Gomez. I'm an industrial engineer.
And I'm John Merrims, and I'm an electrical and computer engineer.
The goal of this project is to create an unmanned aircraft system, or a UAS, that can be used for greenhouse applications. This UAS will need to have a variety of sensors that allows it to fly throughout the greenhouse without the need of human help, and take temperature and humidity sensor readings at each corn crop. The system will also need to be able to send this data to Bayer's computer system in real time. The greenhouse that the UAS will be flying in has a lot of different obstacles that is important to be aware of. The first is that it is flying over expensive crops that takes a long time to grow. It's important that the drone stays a certain distance away from each crop.
The system requirements of the unmanned aircraft system are broken up into 5 major categories. The environmental requirements state that the drone shall be able to operate and fly in a humidity of up to 70% and a temperature range between 50 and 150 degrees Fahrenheit. The drone shall be able to operate while misting is in progress. The performance requirements state that the drone shall be able to record ambient humidity and temperature readings above each planter box, as well as take clear digital and thermal photos of each of the planter boxes. The drone shall be able to do all this and traverse the greenhouse without any human interaction. The safety requirements state that the drone shall be able to hover within 6 inches of a specified height above each planter box to gather the data. It shall also be able to detect any structural beams and walls and avoid these to prevent crashing. The drone must also be lightweight in order to be able to be picked up by a human if it needs to be moved. The interfacing requirements state that the drone must be able to connect to the Wi-Fi in the greenhouse and upload data to the Bayer database. The unmanned aircraft system is broken up into 4 subsystems: the sensors, the camera, the drone, and the computer. The sensors subsystem includes the temperature and humidity sensor, the beacons, and the beacon tag that goes on the drone. The camera subsystem includes the digital and thermal camera. The drone subsystem includes the flight controller and the motor that are inside the drone, the battery of the drone, and the frame of the drone, as well as the sensor casing that goes around the Raspberry Pi and the other sensors. The computer subsystem includes the Wi-Fi adapter, as well as the Raspberry Pi.
For the software design, we implemented a state machine to control the tasking of the drone in flight. For the navigation, we used a waypoint mission, where each plant bench is assigned a waypoint to be visited in flight. A challenge of our software design was how to integrate the internal positioning system, since GPS could not be used in the final product. The state machine we implemented shows the task flow while the mission is being executed. This simulation shows the built-in DJI waypoint navigation mission that's been integrated into our state machine. You can see the vehicle is traveling to each waypoint, but upon reaching the waypoint, the vehicle was locked out of being able to either ascend or descend and simply hovers until moving to the next waypoint. While the built-in waypoint navigation was able to visit each waypoint successfully, it was unable to accomplish all the tasks of the mission, such as ascending or descending to the plants. Also, the built-in waypoint navigation requires the drone GPS, and therefore the internal positioning system could not be integrated into the specific system. This simulation shows a custom waypoint navigation that we developed for our vehicle, where rudimentary flight controls are used instead of the built-in DJI waypoint navigation controls. The flight controls are directed by the distance between the current location of the drone and the target waypoint. This system removed the direct coupling of the GPS and the flight controls in our navigation system, although as you can see, the flight is not quite as efficient and sometimes requires backtracking to reach the waypoint. With the use of our custom waypoint navigation, the mission was able to be accomplished and could be accomplished using an alternative location system. Although we could not directly integrate the IPS beacons into the simulation, we were able to use the GPS in a way to mimic how the IPS beacons would work. Therefore, outside of the simulation, we would be able to use the beacons to drive the flight controls for the drone.
Because of COVID-19, we were not able to complete testing as planned, but this is the final test we conducted instead. We ideally wanted to test this at our sponsor's greenhouse so that we could actually fly the drone, but that was not available. We first set up our beacons in the four corners of the room to create the grid for the position tracking. This is an image of a single beacon, and we had one of these in each corner. Then we set up a waypoint grid with tape at each waypoint so that we could have something to take a picture of. This is our setup on the drone. You can see the mobile beacon on the top, the Pi camera and sensor on the front sort of jerry-rigged to the drone because we could not get the parts to affix them in time for this test. Here's a video showing us actually conducting the test. On the left-hand side of the screen, you can see the program terminal reporting what the system is doing. The program is running from the Raspberry Pi on board the drone and is controlled from a laptop using an SSH connection. On the right-hand side is me carrying the drone through its mission. Since we couldn't fly the drone, me carrying the drone acts like the flight controls for it. If the drone was actually flying, it would be receiving flight controls telling it to move just like I am until the mobile beacon tells that it's in the correct position, at which point it will pause and then continue to its next position. Once we get to a waypoint, you can see on the terminal that we pause, descend, take data, and descend. We also have a cord powering the Pi during this test because we were unable to get the power converter that would allow it to draw power from the drone. This is us receiving to our last waypoint. After it takes data at the last waypoint, we go back to the starting position, and then we'll land. During these final processes that it conducts, it sends our data to a Google Drive right now. This would be going to some database at our sponsor's greenhouse. We were unable to do this testing since we were unable to go there.
This year, we're facing a really unexpected problem, which heavily impacted the direction of our senior design project. We initially wanted to do the integration of the beacons inside the greenhouse, where we also wanted to test our final product. We were also considering having a traditional design day where we could do our presentations in person, but due to COVID-19, we had to do some adjustments, which included presenting a working simulation where we could show that our systems and subsystems work correctly. We also had to demonstrate that the beacons work in a different environment than the greenhouse. And finally, we had to do a video presentation instead of having our traditional design day. The main problems that we had to overcome throughout the semester were working through the quarantine and through the pandemic, and also working with tight schedules due to delayed shipment. Even though we were not able to fully complete and test our system, we were able to create a simulation and model how our system should work. The lessons we learned were that there are a lot of unexpected problems in the real world, and that you need to make backup plans in order to mitigate the risk that those problems might present.
We'd like to thank our mentor, Dr. Ogden, for all the help he's provided us this year, as well as our sponsors, Danny Williams and Jason Licamelli. We'd also like to thank the judges for giving us a chance to showcase our project despite the current situation. Thank you.